Okay, so almost exactly a year ago, Gabor with George over there, they had a presentation about code. Was it code checker, right? Not code compass. I tend to mix those up. So they had a presentation about code checker, which is an open source tool, and this time Gabor is going with more. Going to tell us about more about the Clang compiler, I believe. Yeah. Not only the
also
compiler
GCC
magic, compiler magic. Yeah. These things. You should have gotten 2 coupons for tomorrow's Meetup after party event, I believe.
Looks like this.
Yeah, exactly. That's upside down, but yeah. Okay, so you can use those tomorrow at 9 o'clock at Google Ground. If you will come, we'll be there. So please join us. And Gabor, the stage is yours.
Thank you. So let's talk about compilers. First, what are compilers? Where can we find compilers? I will show you a high-level picture of how compilers look like. And basically what this talk is about, the tools that you should use, which are not restricted to compilers, but as you will see, dynamic and static analysis tools that can help you a lot to be more productive. I will show you lots of demos, so I think some things will break, so be gentle. And yes, so first of all, a compiler is compiling a source language to a target language, and the further these 2 languages are, the more complex the compiler. And compilers are one of the most complex softwares in computer science. We can find compilers everywhere. When we think about compilers, most of the time we think about programming languages, native or interpreted. But for example, machine learning frameworks using compilers to optimize the computation graphs, or we use runtime code generation in big data frameworks. Browsers, in fact, consists of lots of compilers. For example, basically compilers for HTML, compilers for XML, CSS, etc. And even the GPU drivers are basically compilers because they are compiling shader programs on the fly. So when we are looking at the complexity of a compiler, we can see most of the computer science theory in practice. There are some examples on this slide, but this is not very interesting to us in this talk. So the compilers have to do lots of trade-offs. For example, sometimes we want to use less registers. Sometimes we want to be faster. Sometimes we want smaller code. Sometimes we would like to spend more time optimizing, sometimes less. For example, it makes no sense to spend a day optimizing code when the runtime will be less than an hour. But if we are running a scientific application that will run for months or even years, we might want to spend that day on optimizing because it might save us multiple days in the runtime. And sometimes security and performance can also be a trade-off. So how does a compiler look like? First of all, classically, the compiler consists of a front end and a back end. The front end part, which understands the language that you are compiling, and it generates an intermediate representation. And the back end takes that intermediate representation and generates the target program. Of course, the compiler is sometimes doing optimizations. So if we are doing some transformations in this intermediate representation, then we can use those transformations to make this code more efficient. In fact, the optimizer consists of several passes, and these passes can depend on each other, and the order of passes is also very important. And on the front end, you can also have multiple passes, for example, the scanner, the parser, and then the type checker. And when we are doing the code generation, we typically are doing instruction selection, instruction scheduling, and register allocation. But of course, we do not like to do duplicated work. So for example, in case of LLVM, what the compiler developers did, they built a common optimizer, and then we can build front ends and back ends separately. So if we add a new front end, we can use the existing optimizer, and we get most of the optimizations for free. And we can utilize all of the backends that were already written for us. So we can easily target lots of architectures. So the basic idea is that we do not want to duplicate the work, so we are using libraries. I think this is not new, and this is what we usually can read about when we are reading a compiler textbook. But the compiler textbook do not tell us about the real picture, that today we are not only using compilers, but several other tools that are crucial to the success of the software development project that we are working on. So in fact, these libraries are not only utilized inside the compiler, but we have several standalone tools that can help us during our development efforts. And these components are reusing everything that they can from the compiler. So this is what this talk is about. Let's talk about those tools that are rarely taught at the university. Some of them are probably rarely used nowadays at some of the projects. So let's get ourselves more familiar with those. So first of all, when we are thinking about a compiler, what is the expectation that we have for that compiler? And let's look at some little example applications to see what I'm talking about. Probably some of you already seen similar software, so I'm wondering whether someone would like to volunteer what will be the output of this program when I compile it and run it. Any volunteers? I heard that it depends, so let's see. I will compile this program first with GCC. And the output is 22. I will compile it with Clang. I got a warning. And the output is 12. So it's pretty interesting. I have the same piece of code, and the compilers disagree what is the output. So what is happening there? Of course, the code contains undefined behavior, and as you can see in the warning message, there are unsequenced modifications to the same memory location. So basically, because we are not using sequence points properly, in this case, the compiler can disagree on the output. So we want the compilers to generate correct code. And in case the compiler cannot generate correct code for some reason, we would like to see a warning like that. So I would like to avoid being a Clang fan here, so I will show you. In case I'm turning on the warnings of GCC, I will get a very similar warning message. So in this case, the default settings for the Clang was better, but GCC still have the same diagnostics. So let's see what I wanted to show you. Okay, let's look at another example. So this is a little factorial calculating program, and we also would like the compiler to generate efficient code. So let's look at the result of the compilation of this program after optimizations are turned on. So this is the assembly output of the program that I showed you earlier. And as you can see, it did some vectorization to my code, so you can barely understand probably what those registers are. But what is more important, if we check the main function, we cannot see any trace of calling the fact function. In fact, you can see a constant, which is the result of calculating the factorial of 5. So in fact, the compiler recognized at compile time that the execution of the function is not depending on any of the runtime values. So it can do the computation once at compile time and saving time for the users who would like to run this program. So the users do not need to spend any time to calculate this value. It is already calculated and embedded in the resulting binary. Okay, and what was the last one? Here you can see an infinite loop, an infinite recursion, to be more precise. So let's see what happens if I compile this piece of code. I will get a segmentation fault, probably the result of a stack overflow. What happens if I turn on optimizations? I do not get a segmentation fault. I'm getting a program that do not terminate. So what we have seen a piece of code that gave us different results when we used different compilers. We saw a piece of code that gave us different results when we used different optimization levels. And basically that's it. So this is the complexity that compilers needs to deal with. And we want them meanwhile to be fast, want them to generate fast code, want them to generate correct code, and want them to help us find bugs. So for example, if I compile this code with Clang, with all the warnings turned on, I believe I will get a warning that there is an infinite recursion in the program. So it could find this case as well. So let's look at another example. So there is an array in this program, and afterwards I will read a number from the command line arguments and increment every member of this array and then write something to the standard output. Let's see what happens. So first I will use 3 as the command line argument, and nothing unexpected happened, because as you can see, the length of the array is 5, so I will not do, and so there will not be no buffer overflow. I will call it with 6. So I did a buffer overflow, which is of course undefined behavior, but I couldn't observe any change in the behavior of this program. Let's try some bigger value like 10. When I used 10, I could observe a change in the behavior of the program, and I could see the result. I could see the string hello on my output. So as you can see, the side effect that we could observe was at a different place than the error itself. The error is within this loop, but we got the segmentation fault after the hello was written out to the standard output. So the symptoms of the error and the place where we had the error was different. So let's try with another value, which is much bigger. And then I get a segmentation fault before writing the hello string out to the terminal. So as you can see, the same piece of code, which has the same undefined behavior, can provide very different behaviors depending on the circumstances. So if you think about this, this is a bit scary. How can we detect such errors when we cannot be sure where are these errors coming from? How can we detect them if we cannot be sure to reproduce them when the compiler flags are changing? Or how can we be sure to detect them when they can just appear and disappear indefinitely? So basically, the middle age method to avoid this kind of bugs is not writing them. So basically, what we did in the Middle Ages, if you did not comply with the rules, then you will get punished. And this is what happened not too long ago. If you wrote code that contains undefined behavior, then you will be punished. You need to debug that, and that is a very painful process. The Middle Ages are almost over. We now have tools to detect such errors that can help us a lot. But unfortunately, there are still some missing pieces that I will talk about. So most of the talks I saw about the sanitizer and fuzzing, they emphasized the strengths of these tools. I would like to show you the dark side and what is still missing and what we need and what we need to do to get those tools. So first, let's talk about static analysis. Static analysis is analyzing the code without running it. And we can do a lot without running the code. For example, probably one of the easiest tasks at first seems to be the formatting. We can do optimizations. We can emit warnings, which is kind of like the first line of defense. So when we are developing, we always want to turn these warning-related flags on and keep the build clean, so we can spare a lot of time hunting nasty bugs. We can use, for example, clang tidy, which can detect certain kinds of errors and also performance smells. And we can also use it to refactor our code. For example, we can modernize it using the newest standard of C++. And we will look at the Clang Static Analyzer, which is mainly for finding bugs, and it does a much deeper analysis on the source code than Clang Tidy does. So first, let's see a demo about Clang format. So as you can see, there are some very long lines here that I do not really like. There are also some very long character literals. And I don't know whether you can recognize what this macro contains. So so the formatting here is abused, and probably would like to punch the guy who wrote it. Wait until the end of the talk because I wrote it. And this is another string literal within a macro. This is a struct and a function prototype. So let's hit a magic key, and this is what you get. So what I would like to emphasize, it could reflow the comments. So basically, it enforces the column limits that I'm using in this project, and it could also reflow the literals, so I did not need to add the line breaks manually. This is work that I'm very grateful that I do not need to do. And when it did this kind of free flowing within a macro, maybe you cannot see it, but at the end of the line there is a backslash, so it can respect the macros, and it did not transform your code to do something else. So basically, it could also recognize that there is a lambda function in this macro, and it removed the extra line breaks. And also, how many times did you move your parameters of a function to align well? You never need to do that again manually, because you can use a tool to do that for you. And using a tool to do that for you, you can spend more time on the interesting problems. Okay, so basically with the column limits, it is what tech does, but for code. So let's look at the static analyzer. So if we are looking at this code, we can see a memory leak, because in get memory we return a newly allocated memory, and we never free that memory. And we also allocate memory here, and my question is whether this is a memory leak or not. So I saw somebody waving his hands. So yes, the answer is it depends. It depends what function. It depends on what function f does. Function f might actually free this memory, or it might not. So unless we have enough information about the function f, we cannot tell whether this is a memory leak or not. So if we are using Clang to analyze this file, we can see a warning. There is a potential memory leak in the ninth line, and if I go there, it is there. So this is where the return. So this is where it reported, and we can reconstruct what is happening. So probably it could find this memory leak, and it couldn't find this one because it has no information about the function f. So it does pass sensitive analysis, which can take more time than compilation. So usually it is a slower tool than the compiler itself. And due to there are many unknowns when we are analyzing a translation unit. For example, in the case earlier, we cannot tell what function f does just by looking at the translation unit, because it is defined somewhere else. It can be in a library, or it can be in another translation unit. So the static analyzer is usually choosing the conservative approach. So it tries to not to annoy you with false positive reports. So in case an error might not happen, so in case whether there is an error or not, it depends on some fact that we do not know. The analyzer tries not to report these errors. So basically, it values your time. So of course, it is easier for the analyzer to look at the code in some sense than you. So it tries to not to waste your time evaluating false reports. So let's look at the sanitizers. Let's sanitize this very same file. I will use the address sanitizer. I will turn debug symbols on. And I will add the definition of f, which is doing nothing, but we needed to be able to compile this code. So we compiled using the sanitizer, and the sanitizer can find us the memory leak, and it found the memory leak in the 14th line. So let's see where that is. So this is the memory leak that it found. So it could find the memory leak that the static analyzer couldn't, because at runtime the sanitizer has more information. It knew what function f did. So basically it could find this. However, it couldn't find the memory leak that is up here. It couldn't find it because we didn't run this code. So we executed main function, of course, and we didn't call the G function. So basically, because we did not execute that part of our code, the sanitizer couldn't find any error in it. So the static analyzer is good because the static analyzer can have coverage where we do not have any test or we do not have any QA process for that. And the sanitizers are good because they have more information at runtime, so they can detect errors that the static analyzer couldn't. So basically what I try to emphasize is that these tools are best to be used together because both have weaknesses and strengths. Okay, so probably I also would like to show you thread sanitizer. So there is a piece of code that summarizes a vector, and I was very lazy to write any std thread related code, so I just used OpenMP. And basically there is a race condition, so I forced OpenMP to spawn at least 4 threads, and those 4 threads are having a race on the variable sum. So if I try to compile this, and run this, nothing happens. If I add the thread sanitizer, it will print me a nice report about a race condition, and it is long because it gives us the report for all of the threads. So as you can imagine, we either have been very lucky so that all of the 4 threads did access this variable at the same time, or the thread sanitizer is clever enough that it can detect races that did not happen. And I will tell you this is the later case. So if there is a chance to have simultaneous non-atomic or unsynchronized access to a location, the thread sanitizer will find that, unless you have too many threads, but the thread sanitizer is very likely will find that. So the behavior is kind of deterministic, not in all cases, but I will not go into the details how this works. So the kind of deterministic, so you do not need to rerun it several times to get the reports for the race condition. So I also wanted to show you the UB sanitizer. The UB sanitizer can detect lots of undefined behavior like integer overflow, assigning an out of range value to an enum, creating a null reference and stuff like that. So let's see how that works. And it detected that there is a runtime error, there is an integer overflow. So basically it could catch this very silly error that I made here. And you might wonder whether you can use multiple sanitizer at the same time. And fortunately, you can, but not all of them. For example, you can use the address sanitizer together with the undefined behavior sanitizer without any problem. I didn't try all of the combinations, so I will not talk about the other possibilities. And let's look at another example, this piece of code. So I have a two-dimensional array, and I have two assignments. Both of them is out of bound. The first of them is out of bound in the inner array. The second of them is out of bound of the outer array. So let's see what will happen if I'm trying to sanitize using the address sanitizer. This example. Okay, so I will tell you that it is able to find the second out of bound assignment, but it is unable to find the first one. At least this is what you see. But now I will turn on more aggressive optimizations, and now it won't find anything. So what happened? What happened is that this is in fact a dead store. I never read any value from the memory location where I stored this value to. So basically, the compiler will do some optimizations and remove this dead store from my program. After this dead store is removed, the address sanitizer can no longer find this error. So basically, what happens here, the optimizer hides a logic error in my program. So what can happen, I'm using the address sanitizer, I'm using optimizations, and you are always using optimizations. Even if you are telling the compiler not to optimize anything, you are still using optimizations. So the compiler developers are liars. So basically, there is no guarantee the compiler won't remove code from the generated binary. So stuff like this can happen all the time. And what can happen that you run the address sanitizer, you didn't get any report, and then add some new code, for example, reading from the same memory location. The compiler no longer optimizes that store away. So on the next time you run the address sanitizer, you can detect this issue, even though the code you added has nothing to do with the source of the error. So using this kind of effects between the optimizers and the sanitizers can surprise you. So this is something that you should definitely think about when you are using sanitizers. So even when you have very good coverage and you run all the sanitizers, you cannot be sure that your code is correct. So there are no silver bullets. So of course this is one of the shady part of the sanitizer. And also this is kind of a philosophical issue. So it is a very good question whether this code is correct or not. So if it is guaranteed, if the compiler is guaranteed to eliminate the dead stores, would you define this code as correct or incorrect? It's a question that we should not discuss here during this talk, but I think this is something that is a good exercise to think about when you have nothing else to do. So probably never. Okay, so of course, in order to for these sanitizers to be useful, you need to use them with good coverage. And you get coverage from your automated tests, which you have, of course. And you should occasionally run these tests with these sanitizers enabled. Unfortunately, not all of the platforms are supported, and not all of the combinations are supported. And as you can see, optimizations can backfire. So at one of the conferences, maybe Chandler Caruso said that if the compiler optimizes upon certain pattern or behavior, and the sanitizer should find the issue. So, for example, if the compiler optimizes based on the assumption that there is no integer overflows in your code, there should be a sanitizer that find integer overflows in your code. So running that sanitizer, you can find those problems without before the compiler optimizes them away. As you could see from the earlier example, we are not quite there yet. And in some cases, we do not want to be there at all. For example, in some mission and safety critical areas, developers are shipping code that have the sanitizers enabled. So in the release build, some software in the release build have address sanitizer and undefined behavior sanitizer enabled. And in those cases, we want those optimizations to remove the unnecessary checks from those sanitizers. And why is it good to have those sanitizers enabled? Of course, because if you're having a mission critical application, it is sometimes better to terminate the application if something bad happened than producing the wrong answer. Or it is better to, for example, better to fail a transaction to your bank than having somebody stolen all your bank account related data. So in some places it makes a lot of sense to turn these on for release builds. And there will be a bonus slide that there is a very important area in the C++ language that needs sanitizer very badly, and nobody made it yet. It is already proposed. Probably you never heard about it yet, but if we have time, I will talk about it. Okay, and if in case you see a behavior that or an assumption that the compiler is using for optimization and there is no sanitizer for it, or one of the sanitizer doesn't support that use case, then report a bug because it is either an error in the sanitizers or an error in the compiler. So this is what the compiler developers tell us, but do not believe them because they sometimes tell you very nasty lies. Okay, so sanitizers are good if you have good coverage. So you should be able to tell what parts of your code was covered, because if you can't do that, you can say nothing about which parts of your code is tested against out of bound accesses. So basically, you should be able to measure your coverage, because without this measurement, you cannot be sure how, in a sense, how good quality of your code is. There are lots of ways to define coverage, and there are lots of options. For example, in Clang to measure coverage, there is sanitizer coverage, which can be used by separate tools to measure the coverage, and there is gcov-like coverage that is compatible with GCC, and there is source-based coverage. And I think in order to have time for the bonus slide, I will not copy-paste this code into my terminal, and I assume that you will believe that it works. Maybe let's try that. Okay, so I don't believe that you will believe me, so let's try to run this very quickly. Okay, so let's see if I have it in my. Oh, great! So it will be so much faster this way. So what I did, I compiled this memory.cpp with profile instructions generated into the binary, and after that I will run this, and I used an environment variable to define what is the name of this profile, which is foo.proflow, and then I need to do some indexing on this raw data. And afterwards, I can have a very nice output which can show me in red which part of the code wasn't running on the last time I ran this piece of software. So you can have a very handy command line tools to visualize which part of the code wasn't covered. And in case of sanitizer, if that part of the code wasn't covered, that means you cannot be sure that those kind of errors that the sanitizer could catch do not happen there. You can never be sure anyway, so maybe that's not a big problem. Okay, there was sanitizers. Okay, so this was the source-based coverage, and we can also have a sanitizer-based coverage that are used by other tools. Okay, so let's talk about security. You already saw an example where optimizations backfired us. So let's look at another one. Okay, let's look at this one. Not this one, but this one. Okay, so there is some very secret data in this code that I do not want to be leaked out. Let's imagine that this secret data is somehow read or generated, so it is not in the not in the binary when I compile this code. So basically, I would like to do something with my secret data, and afterwards I want to get rid of it as fast as possible. So somebody like a hacker do not have a chance to look at that string which is left in the memory. Okay, so let's see. Okay, let's try to emit LLVM using Clang. Okay, so now I have the intermediate representation for the LLVM intermediate representation for this file, and let's try to view it. I hope I will get lucky. Yes, it worked. So as you can see, let's make it a bit bigger. As you can see, there is a call to memset. So nothing interesting happened here. Okay, so next time I will turn optimizations on. So I will run the optimization passes on this code. And as you can see, after the call to consume, which was my function, there is no call to the memset. So I didn't really get rid of the data. It is left in the memory, and somebody could get it in theory if he's lucky enough. So basically the compiler was right. With the memset, I zeroed out a memory location that I never used afterward. So removing this memset from my program did not really change the behavior of my program. However, it did change the behavior of the system. And in this case, I do not really like that. In this case, this data was sensitive, and I wanted to get rid of it, and the compiler but the compiler was benign. The compiler didn't want to do anything malicious. The compiler didn't want to hurt us. The compiler only wanted to generate very fast code, and it did. But sometimes the compiler is too smart, and we need to be, or too dumb, and we need to be a bit more careful what to tell him. So how can we make sure that this code will not be removed? I wonder if anybody has any idea.
What if we mark that volatile?
Mark what? So the suggestion was to mark something volatile.
String variable, secret key.
The secret key. If I mark secret key volatile, I think yes, then it will not optimize away the code to memset, but it will not do any other optimizations to that memory location as well. So if we mark that memory location volatile, then the code will be secure in a sense that we will zero it out. However, the code will not be fast. So I wonder if there is a way to be both fast and secure.
Are there any
Magic keywords?
assembly inline thing?
It is possible to do it with assembly, although I do not want to do this.
I cannot remember, but there was a CPP-con video.
I think I know what you are talking about. It's about the clobber part of the assembly instruction, where you are saying that this assembly instruction might change anything in the memory, but that is also very bad because it also prevents lots of optimizations. So what the possible solution is, so there are two possible solutions. I'll show you one. One of the possible solutions is that on some platforms there are special memset-like functions that the compiler guaranteed not to remove. But if in case your platform do not have something like that, you can do something like this. So let's see how this works. So we are having a function pointer. The function pointer itself is volatile. So the function pointer is volatile. We set this function pointer to memset, and we are calling the memset through this volatile function pointer. So what does this tell to the compiler? So it tells the compiler this function pointer could be modified anytime from the outside of the program. So the compiler has to assume that somebody can set this function pointer to another function, and that another function might have a side effect that have an observable behavior. So it is not safe to remove the call through this function pointer. If we remove the call through this function pointer, then we could change the behavior of the program. So basically, using this technique, I can force the compiler not to remove calls, while I still enable the compiler to optimize anything else. So this way, I can have both reasonable performance and reasonable security. And I want to have reasonable performance because with reasonable performance, it is harder to hack the code.
Wouldn't it be more easier if you would use the function which uses the data, the maximum, and in that case, then that function would be another
Okay, so the question is, wouldn't it be easier if I just moved the code to the memset to a separate translation unit? And the answer is that the compilers are sneaky bastards and getting smarter every day. So if you turn on link time optimization, then the translation unit boundary is no longer a barrier to the compiler. So it will get smart again and remove your call. So putting the function in a separate translation unit is, so putting it in a separate translation unit might be a solution today, but it might not be a solution tomorrow. And we would like to have permanent solutions. Okay. Other questions?
When you are using memset, I think that some of the compilers that G++, one of them is handle them specially, not as normal library functions, and therefore they apply additional optimizations.
Mm-hmm.
And those additional optimizations might be switched off when you access memset via
Mm-hmm. Yes, so the comment is that, in fact, I also use the term reasonable performance because Zoltan is right that compilers sometimes treat memset and other special functions differently than any other function. So memset specific optimizations cannot happen when I'm calling it through a volatile function pointer. So we still lose some of the optimization possibilities, but not as much as we would have lost if we used volatile on the memory itself.
How about making a function which basically uses a volatile destination pointer? So it takes your destination pointer, casts it to a volatile, and then
I see.
like that.
So the question is, what about if the destination pointer itself is volatile? And I did not think about this, so I cannot answer this.
I mean, not
right
the destination pointer, the thing it points to.
Mm-hmm.
So the pointed thing
Mm-hmm.
is the volatile.
I see. I cannot answer this right now. I think I need to check what the compiler does in this case and how it interprets this, but it might work. Okay, so there are more to the security than ensuring we clean up data correctly. I really recommend this blog post. Hopefully the presentation will be made available for you all, so you can just tweak it. And it has some very good advices how to compile security critical code. So basically, for example, adding address space randomization, stack protection, control flow integrity protection. So there are lots of compiler flags that, of course, makes your code run slower, but also makes it much less fragile against the hackers. So in case your project is security critical, you probably want to use those flags in your release builds. Okay, so let's talk about fast testing. And of course, when we are writing tests, we sometimes forget some of the critical cases. And also, how can we know that we didn't cover something that was important? One possibility would be to run the tests, look at the coverage, look at the part of code that we did not cover, and use this information to reverse engineer what test case did I forget and add this test case. This is a very repetitive work, so the question is whether we can automate it. So basically, this is what fast testing does. So in case of fast testing, we, at least in case of libfuzzer, which is an LLVM project, there are other ways to do fast testing. So about libfuzzer, we are saying that it is a coverage-guided evolutionary fast tester. So what it does, it's using the coverage information, and using this coverage information, it basically have a corpus of test data, or if it has no corpus of that test data, it generates something randomly. You will see it later. And it is an evolutionary algorithm, so it tries to mutate this data randomly and generate new test cases. And if some of the test case did increase the coverage compared to the old ones, it adds that to the corpus. So basically, you are getting more and more tests that can be reused to doing recombines, crossovers, and other mutations among them. And in the end, you will get a large amount of test cases, and some of them might trigger an error. So using sanitizer together with fuzzing is a very good idea, because when you are running this corpus of test cases with the sanitizers enabled, you can catch a lot of undefined behaviors. And there is a YouTube video, and if I recall it well, they are able to find the Heartbleed security vulnerability within minutes using fuzzing. So I prepared a demo for that. Long ago, I had an assignment at the university. I had to write basically an interpreter for lambda calculus. Lambda calculus is a very basic language. Maybe if you know Haskell, it is like Haskell but dynamically typed. Or maybe if you know Haskell well enough, it is the other way now. It's the other way around. So Haskell is lambda calculus-like because lambda calculus was there first. It was created in the early 30s, so it's like a very weird way to write computations. So there is a lambda term which we usually call true, and there is a second lambda term which we usually call if then else. So lambda functions are anonymous functions. So this is where they got the name from. For example, in C++, they were already there in early 30s. So the first function just drops this. So the first function is a 2-parameter function. It drops the second parameter and returns the first one. The second one gets a predicate and it applies. So the second one gets a condition which is called P, and it will apply A and B to the result of this condition. And in case the result of the condition is true, we will drop the second argument, so we will get A. And otherwise, you can imagine the true. The false would be like dropping the first argument and returning the second. It is not important at this point. So the point is that you can use this kind of mathematical notation to write down computations. So we can write an interpreter for that. And let's see. So I have some test cases here. Instead of the character lambda, I'm using the backslash. I'm making the project. And I can feed the test cases. And in some cases, the input was not valid. There were either a syntax error or the normal form, which is the result of the evaluating the lambda expression, do not exist. For example, a computation might diverge and it might never terminate. In that case, I will write out that there is no normal form. So this piece of code was written for an assignment at the university. This code passed all of my test cases. This code passed all of the teacher's test cases. This was accepted, and I got the best grade for this. So let's see if fuzzing can help us to find an error in this code that is not very much. So let's see how much code there is. So it's less than 500 lines of code. So how many errors can be there in 500 lines? when we already tested it throughout. So let's see how this project looks like. So I will only show you the fuzzer because fuzzing isn't free. You need to write code to be able to fuzz. So what libfuzzer does, it gives you one function, this LLVM fuzzer test1 input, which is called several times, in fact lots of times, and you get some random bytes, random gibberish. So and you need to somehow feed this random gibberish into your application. So first of all, there are some cases I do not want to handle, like empty input. I do not care about that. I also do not care about too large inputs because I want the test cases to be easy to comprehend. This is something that I added for this specific case. You usually want your program to work on large inputs, but this is only for demonstration purposes. And of course, you can get any random gibberish, random bytes from this. So what I did, it doesn't make sense to have all kind of funny characters in a lambda expression. So basically, I defined an alphabet up here, and I added a small check. If one of the characters is not inside this alphabet, I will early return. Why is this good? Because during the fuzzing, when there is a new test data generated, and that new test data do not increase the coverage, it will not be added to the test corpus. So in case the new test data contains a character that is not inside the alphabet, it will not be added to the test corpus. So basically, the fuzzer will learn pretty quickly what is the alphabet, and the test cases it generates will only use the characters from this alphabet. And afterwards, I will create a parser, uniquify variables, check whether the expression is closed, reduce it to normal form, and return. So this is how the fuzzer looks like. And let's make it. You can see the command line options in the terminal, but you shouldn't care about this because I would like to make this awful piece of code available. So please do not look at the code itself, only the fuzzer part, because I should be ashamed. Yes, because it is terrible. Okay, so I will start the fuzzer, and it will start to generate test cases. And you can see it creates several, like copy part, change byte, change bit, copy part. So it change big int. It is doing some kind of mutations to the test data. And the fact is, fuzzing is driven by randomness. So I have no idea whether I could find an error in this code or not, because there might not be an error, or even if there is an error, I might not find it because maybe I was unlucky with the random seed. So it might find, it found an error. So it looks like I was able to find an error in a code that was accepted by all of my teachers at a university assignment. So somebody should feel ashamed, but probably it's me because I wrote this code in the first place. So I was the one who made this error. So as you can see, there is some input down there, which looks like a lambda expression. So there is a new file called crash and some gibberish. So if I run lambda and feed the crash, so feed what is inside this file, you can see that it looks like a correct lambda expression. Maybe it's not correct, I did not check that. Probably it's correct. And it really crashes my program. So I was able to find an error in my code using fuzzing. I could fix that, but I have no idea how my code works now because it was written many years ago, so I wouldn't do it here. It is left as an exercise if you would like to correct my assignment. Okay, so there is a... Oh, I didn't save the corpus. So the corpus was... Okay, let's do another run. I should make a directory for that. Okay, that's enough. Let's see what's inside. Okay, so there are lots of files, and if I check what's inside, it looks like that. Maybe it didn't run long enough, but actually in the beginning, these test cases are looking rather primitive, but if I'm running it for long enough, it starts to recognize how lambda calculus looks like, and it starts to create more and more correct lambda terms, and in the end, it will only generate correct lambda terms, and this is all guided by coverage. So basically, this way, guided by coverage, it can learn the input format of our program. So it is also kind of a machine learning algorithm. The problem is that it is hard to test a very multi-layered application. For example, if you were to test a compiler, you were probably... So most of the time you would just generate gibberish, and at some point, probably it could figure out how to generate correct tokens. It might also figure out how to generate correct grammar, but you do not have enough time to have it generating also semantically correct code. So you do not have time for that. So in some cases, you want to use the random data to do mutations. For example, you have like an initial corpus of data, and depending on the random bytes you get, what you will do semantics preserving transformations on this corpus, and then you check whether the result you get is the same that the original example had. This way you can also catch correctness mistakes and not just undefined behavior. Okay, and also you want your application to be deterministic, because if your application is not deterministic, then coverage guidedness makes no sense, unfortunately. So you want your application to be deterministic, to be able to test it. There is link time optimization, which is good. And there is profile guided optimization, which is good as well. So basically, I'm out of time, so I try to be very fast. So profile guided optimization, you, instead of static estimates, what are the hot code paths and what is the code, what should you optimize more, what should you optimize less, where you should spend your optimization time budget. Instead of static estimates, you use runtime statistics. Runtime statistics are still estimates because you cannot know how your user is using your code. So you try to create a typical run of your program so you can have a typical statistic. And there are two ways to get this kind of statistic. One is sampling and one is instrumentation. They are completely separate and cannot be interchanged. With sampling, we occasionally look at the program and see where it is, what it is doing. With instrumentation, we generate program that outputs this statistic. And there is the example, how can I run profile-guided optimization using instrumentation. Instrumentation is more precise, but it takes more resources. So I think if you are interested in profile-guided optimization, you are probably interested in the instrumentation because that's not likely to get you the better results. Okay, so the big picture, you already figured it out. So you want to turn on compiler warnings, you use all of these tools. If some of them are running slowly, you want to put it into the nightly build of the CI instead of running it every time. And on the release builds, sometimes you need to do hardening, and you can use LTO and PGO on release builds only. Yes, and develop fuzzers if your application is safety critical. So the question is whether, so I'm pretty much out of time, but whether you are curious about the bonus slide or not. So who would like to sacrifice some of the social time for the bonus slide? Okay, pretty much almost everybody. Sorry for the others. So let's look at the blog post about strict aliasing. So the bonus slide is about aliasing. If we look at this piece of code, there are two pointers, and these 2 pointers. So we assign 2 values to the pointed values, and we return the one of the values. Okay. So what happens if these 2 values, if these 2 pointers points to different type of values? In this case, the compiler will assume that these 2 pointers cannot alias. So the same one memory location is either an integer or either a long, but cannot be both at the same time. So from this argument, we can conclude that x and y should point to 2 different memory locations. If they point to 2 different memory locations, we can optimize this function to always return 0, because basically this is what we are writing to x. Okay, so this is what's happening. So we always return 0. But what happens if we actually using a cast, and with this cast we are creating aliasing? So here we will create aliasing. So we are pointing to the same direction, and this we first set this memory location to 0, and then we set it to 1. And if we turn optimizations off, we will get 1. If we turn optimizations on, we will get 0. This is because this code contains undefined behavior. We are violating the strict aliasing rules. So basically, there are some more stuff that you should read, and this blog post is great. And there is so many code out there that violating strict aliasing rules that every compiler have a flag to turn strict aliasing rules-based optimizations off. This is called no strict aliasing. So using this flag, the compiler will not do these optimizations. So it will always produce the correct code with the one that I showed you earlier. So there are some little applications that are using this flag, for example, the Linux kernel. So the Linux kernel developers cannot, the Linux kernel developers are afraid to turn this flag off because the Linux kernel contains lots of code that can break these strict aliasing rules. So basically, the compiler can generate much faster code when we omit this flag. But in case you have a reinterpret cast in your code or a C-style cast, then you might violate these rules. So the compiler might generate wrong code. So basically, we are very much in need for a sanitizer for this, and the LLVM community just started to work on one, at least discuss one on the mailing list. And the optimization that based on the strict aliasing rules. Strict aliasing rule is the term that is used in the standard of in the C and C++ standard. And type-based alias analysis is the term that used in compiler land. So basically, there is an upcoming type-based alias analysis, sanitizer, that might help you catch issues when you are doing casts at runtime that can violate these strict aliasing rules. So this is also one point where we're not quite there yet to be able to catch all the errors that the compiler might introduce with optimizations using sanitizers. But if we will have this, probably, I don't know, within half a year. I don't know how fast the community is. I'm not involved in this initiative. So we will get one step closer to the Valhalla where we can find our bugs easily and we do not need to stay up late in the night and all that. So thank you for your attention.